Today a video in the organic analysis series looking at mass spectrometry. So the mass spectrometer is an instrument that we use for the accurate determination of relative atomic mass and relative molecular mass. So essentially it can tell us what the mass of the thing that we are dealing with is. But that's very useful if we have an unknown compound, be able to work out what the mass of that is very easily. Now relative atomic masses are measured on a scale such that an atom of carbon-12 is defined exactly as 12. We talk about referencing it to 1/12 the mass of an atom of carbon-12, and that's exactly 1, and so therefore 12 times that for carbon-12 is defined as exactly 12. Now no other isotope has this mass of a whole number because protons and neutrons do not have relative masses of exactly 1. So carbon's the only one which to a whole number has an exact whole number mass. Now all types of mass spectrometry work by the formation of ions, and these ions are then separated due to the ratio of their charge to their mass. And the whole system is kept under vacuum, and this prevents ions colliding with air molecules, which would obviously get in the way and skew the result. And there's two main types of how we can ionize our molecules. The first is called electrospray. So this is where we have a chemical sample and we dissolve it in a volatile solvent. So volatile simply means that it evaporates quickly, and it is forced through a fine needle. Now what this does is it produces small, positively charged droplets, and they've gained a proton from the solvent. So if we started off with our molecule, call it M, it then gets dissolved in this volatile solvent through the fine needle, and essentially it picks up a proton from the solvent, and so we now end up with an MH positive ion. Now the solvent evaporates from the droplets, and the droplets get smaller and smaller until they contain just the single positively charged ion, essentially just MH+. The other type of ionization is electron impact. This is where our sample is vaporized before being bombarded with high energy electrons from an electron gun. Now what we mean by an electron gun is a hot wire filament, which when we pass a current through it emits electrons. So it acts essentially as a gun that fires electrons. Now this normally knocks off one electron from each particle and produces the +1 ion. So if we started off with our molecule being M, this simply just knocks off our electron to become M+. And so we can write an equation for this. The key thing is that we said the sample is vaporized, so it has to be gaseous. So if you ever write these equations out, always make sure that all of your chemical entities are in the gaseous state. And so if we have our molecule here called A, gaseous, we fire an electron at it, and that will kick off an electron. We make the A+ ion, again, gaseous. And then to make the charges balance on either side, we have to have 2 electrons on our right-hand side. The idea being there, you can see that you have 1 electron on the left, 2 electrons on the right, and so this electron that we've used to knock off from the electron gun has knocked off an electron from that molecule. Now a small amount of 2+ ions can be formed as well, and this is where in our sample here we've not just got the actual molecule A, but eventually we'll have some A+ flying around as well. And so the A+ can also be hit by an electron, and that can knock off another electron. And so we end up now with a 2+ ion, and again we can write another equation here. A+, again remember gaseous, we have to write everything as being gaseous, plus an electron. This knocks off an electron, so it produces the A2+ gaseous ion, and then 2 electrons to balance the charge. So let's have a look now at what happens in a mass spectrometer, and quite often these ones are actually called time of flight, TOF, mass spectrometers. So the first thing is that we need to put the whole system under vacuum. Remember that was just to get rid of all the air molecules, we don't want our ions to be colliding with them. And we inject our sample, and the key thing is that we have to vaporize this sample. And so we either do it by the electrospray method of dissolving it in the volatile solvent, which then evaporates essentially, or we vaporize our sample directly if we do the electron impact type of ionization. But the key thing is it has to be gaseous and it has to be under vacuum. The second step is the ionization that we've just talked about, either through electron spray or electron impact means. So either way, we're going to create a positive ion. The electron impact is to simply use an electron gun to knock off electrons to create the positive ions, M+. Our electron spray was to dissolve it up in a volatile solvent. It picks up a proton from that solvent, and so we create the MH+ ion. The third step is then acceleration. So once we've made these positively charged ions, they are attracted towards a negatively charged plate. So we have simple sort of ionic charge attraction here. And so they get accelerated towards it by that electrostatic attraction. Now, as you can probably imagine, the lighter the ion is, the more it accelerates, and therefore by the time it reaches that negative plate, the higher the speed it has achieved. If we also have a more highly charged ion, that also is going to reach a higher speed because there's greater electrostatic attraction. The fourth is ion drift. So once we've now attracted these ions to the negative plate and they're now moving at a certain speed depending on their charge and their mass, the ions now pass through a hole in this negatively charged plate, and essentially they form a thin beam. And this beam travels along the tube called the flight tube to the detector. And you can see in that sort of the diagram at the bottom here, that's thing called the flight path. It's the same thing. And then finally, the last step here is detection. You can see in the schematic at the bottom, we have the ion detector. So lighter particles have higher speeds, as we've said. You can imagine it being there's less mass, it takes less energy to move them. And so they reach the detector first for the same charge. So if I have a particle that has a mass of 2 versus a particle that has a mass of 10, if they're both 1+ ions, clearly the one that has the mass of 2 will reach the detector first because it has a higher speed. Now the flight times are recorded. That's how long it takes for the ion to move from that negative plate where it goes into the beam, the ion drift bit, to the detector. So essentially it's how long it takes it to go through that flight tube or the flight path part of it. Now, once these positive ions hit the detector plate, electrons flow to neutralize that charge, essentially, to create back the neutral molecule. And so the positive ions accept the electron. When we have an electron flow, that's a current. And so our computer that we've linked this to can read this current measurement. And so the signal from this detector is fed to the computer, and this generates a mass spectrum. And clearly you can think about that the more of the type of ion that we have hitting it, the greater the electron flow will need to be to neutralize that charge, and hence the greater the current, we'll see that the intensity of the peak that we get is higher. So the main stages here really are ionization, either through electron spray or electron impact, acceleration, where we move them towards a negative plate by electrostatic attraction, ion drift, where we pass through the hole and we measure in a time of flight mass spectrometer, we measure the time it takes for them to go from that negatively charged hole to the detector. And then finally, we have our fifth stage here, which is detection. And so this is the electrons flowing to the positive ions, and that flow of current is what we eventually get changed into our mass spectrum. Now, there's another type of spectrometer that you may come across where actually there is a curve in the spectrometer. And so this is where the ion drift step is slightly different. Again, all the steps before it will be the same, and the ions do pass through a hole in the negatively charged plate to form the thin beam. But rather than being sort of measured in terms of time, instead what they'll be measured in is there's a magnetic field which will cause the ions to be deflected round this bend in the spectrometer. Again, we can have this idea that the lighter the ion is, the more easily this can be moved, the more easily that it can be sort of bent around this bend. And so therefore we end up having the ions hit different places on the detector depending on their mass. But for a time of flight spectrometer, essentially this flight path here is a straight line essentially, and we're just measuring how long it takes for the ions to get from that negatively charged plate to the detector. So this mass spectrum is produced from the detector signal. On the y-axis, we have something called relative abundance, essentially how much of that particular ion there is. And on the x-axis is the mass to charge ratio, sometimes called m/z, so m being mass, z being charge. So it's the mass to charge ratio, and often it's measured in something called Daltons. Now, if it's a +1 ion, which the majority of these ions are, it's very rare really that we get a 2+ ion. Because the majority are 1+ ions, this mass to charge ratio very often is just the mass of that ion. If we have our mz, mass divided by 1 is just the mass. And so most of the time we can think of the x-axis really as being just the mass of the species. Now, mass spectrometry can be used for the determination of relative atomic masses of elements. So we've talked in previous videos on the sort of amount of substance topic that the way that we get to the AR value that you see, the atomic mass value that you see on the periodic table, is to do a mass spectrum of that element, and we have to take into account all of the naturally occurring isotopes. And so it's really useful for isotope analysis. Different isotopes give different peaks because they have different atomic masses. They have different numbers of neutrons, remember, for an isotope. Same number of protons, different number of neutrons. And so if we look at these examples here, the first one on the left is for neon. Now, if you look at your periodic table, you will see that neon has a relative atomic mass of 20.2. However, if you look at the mass spectrum, you'll see that there's not actually a peak at 20.02. There's a very, very large peak at 20, very, very small peak at 21, and a slightly bigger peak at 22. Now, we said in the atomic, amount of substance topic videos that if we're going to work out this relative atomic mass from our isotope abundances and from mass spectrometry, that we have to essentially do the weighted average of all of these peaks that appear. So the reason that the value for it is 20.02 is because, as you can see, it's basically all 20, very little of 21 and very little of 22. And if you do a weighted average of all those, you end up with an answer of 20.2. And so the way that you'd work this out is simply do the whatever the mass is, so in this case 20, multiplied by the abundance of that ion. So you do the 20 multiplied by the 90.9 plus the 21 multiplied by the 0.3 plus the 22 multiplied by the 8.8, and your answer would come out to be the mass, which is kind of the weighted average of it, to be 20.2. Some of them are much more complicated. So in the middle is germanium, and if you look at your germanium on the periodic table, you'll see that it has a mass of 72.6. Again, there's no actual peak at 72.6 because the 72.6 is the weighted average of all the isotopes of this element, all the naturally occurring isotopes. And you can see here that in red you have this relative intensity, in the blue you have the isotope abundance. Now what you'll also see is that your relative intensity values, one of them is 100, even though the isotope abundances aren't. And so typically the way this works when you do a mass spectrum is that you will get out your kind of relative intensity of the peaks, and then these relative intensities will be scaled so that the largest peak, in this case at 74, it's scaled so that it's 100. That becomes 100, everything else gets scaled along with it. And then finally, over on the right, we have the mass spectrum here of chlorine. So if we're just looking at an atom of chlorine, remember we have to be careful with our distinction here. We're talking about a molecule, Cl2, or an atom. We're talking here about an atom, just Cl. Now, if you look at your periodic table, you'll see that chlorine has an atomic mass of 35.5. Again, you'll see there's no actual peak at 35.5. There's no actual atom of chlorine that has a relative atomic mass of 35.5. But instead, the two isotopes are, we have chlorine 35, roughly 75%, and chlorine 37, roughly 25%. And so if we do the weighted average of those, the 35 times 75%, the 37 times 25%, the weighted average comes out to be 35.5. Now, all of these mass spectra that you see above here are what we call low resolution mass spectrometry. Now, this shows masses to the nearest whole number, typically, sometimes to one decimal place, but normally to just the nearest whole number. We can also use something called high resolution mass spectrometry, and this can measure masses to 3, 4, sometimes even 5 decimal places, so many, many more decimal places, and this allows much more accurate determination of a compound's formula, Because remember we said on the previous slide that it's only carbon-12 that we define to have that completely round number of 12 as an atomic mass. Everything else will have some, will be a whole number. Even if it takes 3 or 4 decimal points to get there, we will have a slight difference compared to just a whole number. And so, for example, if we have a relative molecular mass of 200, well, that could be C10H16O4, C11H4O4, C11H20O3. And so with low-res mass spectrometry of just giving us an MR of 200, well, that's not so helpful. It could be a number of these organic molecules. If it's high-resolution mass spectrometry, well, as we said, the isotopes of all the atoms apart from carbon-12 don't have exactly whole number masses. And so we would be able to have, it might be that all of these are 200 point something, but it could be that it's 200.001, 200.005, 200.007. And so you'd be able to tell, based on high-resolution mass spectrometry, which one you actually had in your sample. Now, we can use these isotope patterns from the mass spectra that we get out for our elements, and this can help us identify the elements that we have. So, as we've just said, chlorine has 2 isotopes, 35 chlorine, which is 75% abundant, and 37 chlorine, 25% abundant. And so, as we've just said on the previous slide, that's why we have our relative atomic mass for elemental chlorine to be 35.5, because we do 35 times 0.75 plus 37 times 0.25, and so this weighted average comes out to be 35.5. Now, this is quite useful because the mass spectrum of chlorine, or any compound that contains a chlorine atom in it, will be quite distinctive, because you will be able to see 2 peaks in a 3-to-1 ratio of intensity that are 2 MZ units apart, 2 Dalton units apart. And so it's not only useful for identifying the actual atomic mass of chlorine, it's useful to see if we have any chlorine in our organic compound, for example. Because we would look and we would see 2 peaks that have a ratio of 3-to-1 in terms of their intensity that are 2 units apart on the x-axis. Now, this is also true of other atoms. Bromine is another example. Bromine has 2 isotopes, 79 bromine and 81 bromine, and these are roughly 50% abundant each. And therefore, bromine atoms can also be spotted if you have 2 peaks that are 2 MZ units apart, like the chlorine, but this time they are of basically the same intensity. Now, if we go back to the chlorine, for example, typically we won't just have our chlorine as our atoms, but the chlorine atoms will combine covalently to form our chlorine molecules. Remember that it will achieve a much more stable electronic state if it goes from being a chlorine atom into being a chlorine molecule that is sharing electrons. Now, these chlorine molecules are called molecular ions, and there will be 3 of these because of the isotope variations of chlorine. So we have our ionized chlorine molecules, Cl2, kicked off an electron, so it's Cl2+. Quite often you'll see it written as Cl2 plus dot. Now, the dot just represents it's a radical. Remember that a radical is an unpaired electron. So our chlorine originally would have had a complete set of, our octets would have been filled. We've kicked off 1 electron, and so somewhere in that molecule we have an unpaired electron. So these molecular ions are often called plus dot molecular ions because they are positively charged and they are radicals. So we then have to think about the isotope variations of chlorine. If we have a Cl2 molecule, there could be 2 atoms of chlorine that are both the 35 isotope. This would have an MZ of 70. We could have 1 35 and 1 37, or we could have both of them, being 37 chlorine atoms. And so the intensities of these can be calculated by multiplying the abundances and then adjusting the ratio to being 100%. And so if we look at the example here, the way we do it very simply is by multiplying what the probability of each of these would be. So we multiply these probabilities, the percentage abundances of these isotopes together. So if it's both 35, well, our 35 percentage, remember, was 75% abundant. So we do 0.75 times by 0.75, and we get 0.563. We can then have our example of it being a chlorine 35 and a chlorine 37. Now this one's slightly interesting because it could be that if we have to think about a chlorine molecule, the atom on the left could be 35, the atom on the right 37, or the atom on the left being 37, the atom on the right being 35. So essentially there's twice the probability that this could happen, because the atom could be on either side, each isotope could be essentially on either side of that molecule. And so we do our 0.75 times by 0.25, but this time we have to multiply that by 2 itself, because essentially there's two ways that could happen. There's twice the probability. That comes out then to be 0.375. And then finally, we have the example where they could both be 37, chlorine 37. And so we do our 25% abundant multiplied by 25% abundant, and that gives us 0.0625. And then the way to scale these so that you end up with one of them being 100 is to find the biggest one, in this case the 0.563, and divide it by itself. So we do 0.563 divided by 0.563, that's 1. If we times by 100, that would be 100%. And so we scale that one by dividing it by itself. We scale the 0.563 up to 100%. Then for our next one, we have 0.375. We then need to divide this also by the biggest one, 0.563, times by 100, and our percentage here comes out to be 66%. And then finally, we do the same thing with the last one, the 0.0625 divided by the 0.563, and this comes out to be 11%. And you can see then on the mass spectrum on the right that your MZ of 70 is 100, the MZ of 72 is roughly about 60%, and the MZ of the 74 is very low, about sort of 10%, which is exactly what we've calculated. So we now get to how to describe a mass spectrum, because there's a few key terms that we really should know in being able to describe what we see. And so here on this slide we have an example of the mass spectrum of ethanol. Now you can see that ethanol is a pretty simple organic molecule, only 2 carbons long, and alcohol, pretty simple molecule. But the mass spectrum looks quite complicated. Now the reason for this is something that we'll discuss on the next slide of fragmentation. We don't just see a peak for the molecular mass of the ethanol, because when we do our ionization, when we either fire our electrons through the electron impact, or we dissolve it up into solvent, pick up the solvent in the electrospray, it's quite common that our molecule actually fragments, it breaks apart, typically more so in the electron impact, because if we're firing electrons, once we've made our molecular ion, our M plus dot for the electron impact, it's very common that maybe another electron might hit it and it might split into 2 species. And so we see these smaller MZ values because of fragmentation, the ethanol kind of breaking apart. Now the tallest peak, this one that we end up referencing to be 100% of our relative intensity, is called the base peak. This is the most abundant fragment that we have, and so typically it will be very stable, the most stable fragment that we have. And as we've previously said, whatever we end up working out our ratios of these ions or fragments or whatever it might be to be, the base peak always has an abundance of 100%. The peak that's furthest to the right is what we call the molecular ion. So this has the mass of the complete compound. So this is one that hasn't fragmented, it's just been ionized and made it through. Now, the key distinction here is whether you've done electron impact or electrospray ionization. If you've done electron impact, where we've fired our electrons from our electron gun to ionize, kick off the electron from our molecule, let's say we started with our molecule being M, we've kicked off our electron, and so our molecular ion is what we call a radical cation, M plus dot. It's a positively charged ion, and because we've lost one electron, it's a radical, so it's M plus dot. Now the radical bit of it essentially isn't so important. The really key thing, remember when we talked about the stages, was that we have to accelerate our ion. That isn't going to be due to the radical part of it, it's going to be due to the positively charged part of the ion. And then when we get to the end of the steps, we have to accept electrons to become back to M, essentially, and that flow of electrons is the current that we measure. So we have to have the positively charged bit is the bit that we measure. So the positively charged bit is the important bit, not the radical bit. But the truth is that it is a radical cation. If you're doing electrospray, remember that we dissolve it in our volatile solvent, we pick up a proton from the solvent, and so we end up with an Mh plus molecular ion. So it's a positively charged ion, still gets accelerated, still accepts the electrons to have the flow of the current, but we've picked up the proton. So if, for example, let's say the molecular mass of your compound is 66, if you're using electron ionization, your molecular ion will come at 66, electron impact, it would come at 66. If you're using electrospray ionization, it would come at 67. And you have to remember that the molecular ion that you see technically isn't the actual mass of your compound, you have to minus 1 in order to get that. And the final thing to say is that there will always be a small peak, 1 MZ unit, to the right of the molecular ion. And the reason we see this is because of the carbon-13 isotope of carbon. So a very, very, very small amount of carbon is actually carbon-13 rather than carbon-12. And so even on this mass spectrum of the ethanol, you can really barely see there's actually a peak there at all, but there is 1 MZ unit next to the molecular ion. So the molecular ion tends to be, as you can see here for the ethanol, it's actually not a particularly big peak, but it is certainly sort of big enough, roughly about 25%. Next to it, there will often be a very, very, very tiny peak, which is due to the isotope of carbon-13. But the really key thing to take away is that your furthest right is the molecular ion. The highest peak, the 1 to 100%, is the base peak. And we just have to be careful with our molecular ion. If it's electron impact, the molecular ion is our radical cation, M plus dot. For electrospray, the molecular ion is Mh plus. So it's got 1 extra MZ unit. We have to take 1 away to get our actual mass. So finally, here to talk about fragmentation. So fragmentation occurs as when our compound is ionized, some of the bonds can be broken, and hence the ions can break up into smaller ions. Now these fragment ions, as we said, are also detected in the mass spectrum, and they can help deduce the identity of a compound. Often it's the fragmentation that can really help you to identify what your compound is. Now, as we said on the previous slide, if we're doing electron impact ionization, molecular ion is a radical cation. And so when this fragments into 2 smaller species, actually you can imagine it kind of being split down the middle, and essentially what we end up having is one of it being a radical, one of it being a cation. So we have our radical cation, imagine splitting the name directly in half, one of them becomes a radical, one of them becomes a cation. Now it doesn't have to be that our molecule is split exactly down the middle, but the way I always think of it is just the name, radical cation, split down the middle, one of it's a radical, one of it's a cation. And as we said, it's only the cation that is detected in the mass spectrum. Remember, for our ions to actually be accelerated, we need them to have a positive charge. It's electrostatic attraction that does that. And for our ions to be detected, well, they have to be ions, they have to be positively charged ions, because they accept an electron, and that flow of the electrons is the current that we measure. So our radical just doesn't get detected, gets sort of lost from it essentially. It's only the cation that we detect. And that's the same for the electrospray ionization as well. When that fragments, it's only the cation that we detect in our mass spectrum. And so here we have the mass spectrum of ethanol again, and we can start to look at some of the peaks. Essentially, a little bit of it is a bit trial and error, sitting there with a calculator and working out lots of different numbers to see whether they fit. So we have our base peak that we can see here. Remember, the base peak is the highest peak to 100, and we can see that comes here at 31. So whatever 31 is likely to be a fairly stable species. And then we have our molecular ion, which we can see here, the furthest right peak is at 46. So sometimes it's useful to draw out a table like this and to write down essentially what the MZ value is, what the species that we detect is, the positively charged cation, remember, and what the species we've lost is, the radical. So the 46, the molecular ion, the species will be the actual compound, essentially just having lost an electron, being ionized. So that's our ethanol, CH3CH2OH. And remember that our molecular ion, imagine this is done through electron impact, is a radical cation plus dot. We then have a slightly bigger peak here, it's 45. This typically will be the loss of a proton. So we've only lost one MZ unit. The way to think of it is to start from the MZ of the species that is the molecular ion, and just start sort of chopping off parts of it to see if they match. So if we've lost one MZ unit, we must have lost a proton. And so typically we can write this out either as C2H5O, we've lost the proton from the OH group, or CH2CH2OH, we've lost the proton from the CH3 group at the end. The key thing is, though, we've lost a proton, so those are positively charged cations, and we've lost our H radical, H dot. Now, you don't have to go through and analyse every single peak. Really, you're only interested in the slightly larger peaks. So these peaks that are here at sort of 43, 42, we're not going to bother with. Go down to our 31. If we look at the difference between 46 and 31, well, that's a difference of 15. If you see a difference of 15, it's very often that you've lost a methyl group. You've lost a CH3 group. And you can imagine that that would be a fairly standard thing to happen here. We have CH3, CH2OH. You can imagine that that carbon-carbon bond, CH3-CH2 section, can break. And so if we do that, we end up with our CH2OH cation. That's clearly our most stable species. And then we have our CH3 radical that is lost. And 30, again, a fairly simple one to work out. We've started from the one before with 31. We've gone down to 30. If we've lost one MZ value, we must have lost a proton. And so we can lose the proton from the OH group and end up with CH2O as our cation. And essentially what we've really lost from the starting molecule is CH4, a methane radical species. We can then carry on going down, so 29, again, we can start to work out here. If you work out the numbers, you can end up with CH3, CH2. Now, the reason why, essentially, you could look at that and go, okay, if I had 30 before, and I've now got 29, I could have CHO. But you can imagine that taking the proton, taking the H radicals just off that very small unit probably isn't going to be very feasible. Other ways are to look at what else you could lose. We'll go back to the starting ethanol molecule. We talked about the idea that you can take off the CH3 group from the one end. That looks like that could probably happen. Go to the other end. You could probably take off the OH group. So that would be a loss there of 17, sorry, for the OH group of 17, 16 for the oxygen and 1 for the hydrogen. And so if you take 17 from 46, you get 29. And so there's our species. We've lost our OH radical. 28 could then be a proton being removed, an H radical being removed, so CH2, CH2 plus, and we lose essentially an H2O dot species. And then finally our MZ value of 15. Quite often with these things you can kind of flip them around. So we had earlier that we'd lost 15 from going from 46 to 31. Loss of 15 is very often CH3. And so in this case, what we're now measuring at 15 is the actual CH3 cation, and therefore our radical that we must have lost must have been the CH2OH. But you can see that the peak here at 15 is much, much smaller because we said our CH2OH is a very stable cation. It's the base peak, it must be stable. So it's more likely to happen the other way around. So time to have a go at some questions to deal with calculating atomic masses, molecular masses using mass spectra. And so if you'd like to have a go, pause the video and the answers will be on the next slide. So the first one I'm going to start with is the one on the left here. So we had a mass spectrum of a hydrocarbon that's been produced by electron impact ionization. The first one is to say what is the relative molecular mass of that compound. So we need to look for our molecular ion, our furthest right peak. That's what the mass of our compound is. And because it's done through electron impact, we can just take whatever that molecular ion is. Remember that if it's electrospray, it's an MH plus molecular ion, so we have to minus 1. If it's electron impact, it's an M plus dot radical cation, and so it's just the mass. And so our furthest right peak here, we can see is 56. We're then asked why are there peaks with much lower MZ ratios? Well, fragmentation occurs. We said that once these things are ionized, fragmentation can occur because some of the bonds might break. Another reason could be that we have 2+ ions. So we said that most of the time we have 1+ ions being formed from the ionization, but that 2+ ions were a possibility. They're just much less of a possibility. Well, if I have a 2+ ion, my MZ essentially is going to be half what I think it is. If I have my positive cation having an MZ of 50 as a +1 ion, the 2+ ion will have its MZ at 25. And so sometimes you can look at some of the smaller ones, double up those MZ values and see if there's a corresponding peak at twice the value. It doesn't always mean that it's a 2+ ion, it could be a separate fragment. But generally, the low MZ values are either 2+ ions or due to fragmentation. And then finally, why is there a peak or peaks with higher MZ ratios? And so if we look back to our mass spectrum, we said that the molecular ion was 56. There is a slightly smaller peak to the right of that. And the reason for that, the peak at 57, is because we either have the presence of carbon-13 or of deuterium. So that's 2 hydrogen rather than 1 hydrogen. Typically, it's normally carbon-13 rather than deuterium, but 2 hydrogen is another isotope of hydrogen, pretty low abundance. And so it's the presence, really, of either of those. Then moving to the right, we had our mass spectrum of gallium being shown. What isotopes are present in that sample? So remember that the mass spectrum isn't going to show us what our actual atomic mass of our element is, because that's the weighted average that we see on the periodic table. What it is going to show us is what the individual isotopes, the naturally occurring isotopes, atomic masses are. And so if we look where our peaks are, we have one at 69 and one at 71. So the isotopes that are present are 69 gallium and 71 gallium. We're then asked to calculate the relative atomic mass and give your answer to the appropriate number of significant figures. And so the way to do this again, remember, is the weighted average. We take our isotope number, multiply it by the abundance of that. And so we have 69 gallium being multiplied by 0.601. We have 71 gallium being multiplied by 0.399. And that gives our answer to 69.8. Remember that we always give relative atomic masses, relative molecular masses, to 1 decimal place. So in this case, that's 3 significant figures. And then finally, the question in the box at the bottom in the red box says that we have high resolution mass spectrometry of a sample of propane indicated it was contaminated with traces of carbon dioxide, and use the data in the tables to show how precise MR values can be used to prove that it contains both. So this again is an example where low-res mass spectrometry, giving it to the nearest whole number, would be an inconclusive answer, because actually both low-res answers here would be 44. And so you wouldn't know whether you had propane, pure propane, or whether you had pure carbon dioxide, or whether you had, in this case, it's wondering, do I have propane that's contaminated with carbon dioxide? However, using high-res, we can actually tell the difference. So all we have to do is just add all of the same way that we'd calculate a molecular mass for anything else, we just add together the relative atomic masses of all the elements involved. But here you can see that our relative atomic masses are to 5 decimal places, so very, very accurate. And so for propane, we have our 3 carbons plus our 8 hydrogens, and this gives a relative molecular mass here of 44.06352. Now, while we've said previously that we always give molecular masses to 1 decimal place, we always essentially give it to whatever the number of decimal points is in the question in this case. So here we have our atomic masses being given to us in 5 decimal places, and so we give our molecular masses to 5 decimal places. And that's the really important thing for the high resolution here, that we can actually tell the difference. For carbon dioxide, we have 1 carbon and 2 oxygens, and that comes out to be 43.98982. And so you can see that to a whole number, they're both 44, but actually to a few decimal places, here in this case to 5 decimal places, they are actually different molecular masses. And so if you took a very high resolution mass spectrum, you would see 2 molecular ion peaks, one for the propane, one for the carbon dioxide. So thank you for watching this video. You can find many more videos like this on my YouTube channel. If you found the video helpful, please consider leaving a review on a tuition website. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, you can always feel free to drop me an email. I'll be happy to help.